In this video, I'm going to talk about a methodology for dose calculation in megavoltage photon beams. So as you can imagine, this is quite fundamental to radiation therapy physics. So I hope you pay attention and take the time to master this. I think, really the way that you will learn this deeply is to do problems. So I encourage you to go through the problem sets and do all of those problems that you can, so you really try to get this down firmly. Okay, here we go. So the goal here is to calculate the number of MU, that's the number of monitor units. Remember, the monitor unit chamber is that chamber in the head of the linear accelerator that monitors the dose. And so given the dose and the TMR, I should be able to find out the MU, so I can program into the machine to deliver a certain dose. So there's a simple formula for this. So we just take it equal to the dose in centigrade. Remember, this is the dose at this point, at the isocenter point. That's what we're calculating for right here. It's divided by a reference value. That reference value is the number of centigrade per MU under reference conditions, and it's typically 1, times SC, collimator scatter factor, SP, phantom scatter factor, and the TMR, which depends on the depth and the field size. I'll explain what these SC, SP factors are in a minute, but let's just take a simple example. Say we wanted to calculate the number of MU required to deliver 200 centigrade to the isocenter point if the patient was set up to where the isocenter is at a depth of Dmax for a 10 by 10 field. Now for a 10 by 10 field, SC, SP, under these conditions, those are both 1. The TMR at a depth of Dmax is 1. And so it would be 200 divided by 1, 1, 1, and 1. And so it would be, the MU would be 200. 200 MU delivers 200 centigrade under those reference conditions. So you can see if it was 1 centigrade, it would be 1 MU to deliver 1 centigrade. That's because that is the reference condition. 10 by 10 field, isocenter, depth of Dmax. If you start to deviate that, it differs. So, for example, a 200 centigrade to a depth of 10 centimeters, it would be 200 divided by 1, divided by 1, divided by 1, divided by the TMR. So say the TMR is 0.75, let's say. So it would be 200 divided by 0.75. That would give you the number of MU. Okay, so there are also some other factors on the bottom that are sometimes needed. Let me write those out. So you have the wedge factor, if there's a wedge in the beam, the OAR, the off-axis ratio, and also the tray factor, if you have a tray in the beam for blocks. So I think I'll run through an example of how to do a calculation, but first let me explain a little bit what these SC and SP factors are. So you'll remember from video 9.1 that we talked about the collimation system of the linear accelerator. We talked about how there are the jaws out here that define some field size, and then there's some blocking. And the blocking might be accomplished with MLCs, and we had a whole sort of discussion about that. So these SC and SP factors are related to those. So the SC is the scatter factor, scatter radiation that comes from the collimator system, in particular the jaws. And then the SP factor is the factor that comes from the scatter in the phantom. So that is the radiation field that actually is open inside the phantom or the patient. And so that's the collimated field, the field with all the collimation in it, the blocking and everything, so this inner field. So those are the two different factors. So SC, the open field with jaws, SP, the blocked field with all the blocking, MLC blocking in it. So let me rewrite this formula up here at the top. This is a very important formula relating dose to MU. So let me write it out very neatly. And then we're going to run through an example of how you might do a calculation for monitor units. So let me draw the setup first. Here's your source. Here's the patient down here in the ISO center. And I'm going to have this setup be here at 90 SSD. And we want to calculate the dose at ISO center, which is at a depth of 10 cm. Okay. We're going to consider here a 10 by 10 field. And then this field is going to have some blocking that I'm going to draw here. That's going to be blocked with an MLC. So that's the question. What is the MU setting to deliver this dose at isocenter? So the MU, we're going to use our formula. 150 centigrade divided by these factors. So 1, which is number of centigrade per MU. SC, that's, remember, the collimated field, so 10 by 10, the jaws. SP, that's the phantom irradiated region. So we have to figure out what the equivalent square is of that one. And let's say in this example we get that's 9.5. So we're going to use SP of 9.5 by 9.5 field, and then the TMR, and this would be the TMR for this energy at a depth of 10, and this irradiated field size, so the 9.5. There's no wedge, so that's 1. There's no off-axis ratio because we're going to calc at the isocenter, so that's 1. And then the tray factor is 1 because there's no tray. We're using MLCs. All right, so to do a problem like this, you need to know what these factors are: SC, SP, and TMR. You don't necessarily know those. You got to look them up. So SC is easy, actually. This is 1 because the definition for a 10 by 10 reference field is 1. And SP, if I looked it up in a table, it would be 0.99 in this example. These factors are usually close to 1. And then the TMR, again, I have to look that up in the table. And when I do, I get 0.81. So you got all your numbers. You can plug and chug. 150 divided by 1 divided by 0.99 divided by 0.81. And you get 187. So that's your answer. That's what you would program in to get this dose under these setup conditions. All right, so let's consider a slightly different setup here. Same isocenter, but the patient now is set up down here at an extended SSD, here 110 cm. And again, I want to calculate the point here. So the dose at that point, which is the same point, a depth of 10 cm in tissue, but now it's not at isocenter anymore. So how do I do that? Well, what you do is apply basically an inverse square factor to move that point away from the source. So you multiply the MU by, in this case, 120 divided by 100, and that's squared. So to move it from where it was out to 120. So I actually, in this formula, to make it more general, I should add this inverse square factor up here in case you need it. So here's what the formula looks like with this inverse square factor. And you can see that in the first problem, if I did it with this formula, I would have had SSD of 90 plus a depth of 10. That would be 100. So it would be 100 of 100, and this factor would just be 1. And so it was the same as the first formula that I wrote. All right. Now, one final thing is that you might want to think about that we're using TMR here. But remember, I talked a lot about PDDs. So can you use PDDs? And the answer is yes, you can. And here is the formula. So here you can see that TMR has essentially been replaced by the PDD in this formula. Okay, so this is most useful in a setup where it's SSD setup. So like a figure like this, where you set up the patient at some SSD and you calculate the depth in tissue, or the dose at some depth D. You also have to apply this factor in the formula here, and that's because the reference dose of the LINAC is probably not defined with an SSD setup, but rather it's SAD at isocenter, so you do inverse square. So let's consider the case where this SSD is 100, because that is a common case. You often might commission or measure PDDs at an SSD of 100, and in that case, the formula reduces to this. So that's how you would do PDD-based calculation. So one other final thing about all these equations is hopefully it's obvious that you can calculate the MU if I tell you what the dose is. Also, if I were to tell you what the MU are, you could calculate the dose. And you would just invert this equation to figure out what the dose is. All right, so I'm going to move on in the next section and talk a little bit more about some of these factors, but let's take a little pause. So let me spend a minute here talking about equivalent squares. So say you have a rectangular field here. It has some length L and some width W. You want to figure out what is that equivalent to radiologically in terms of a square with some side S and another side S. So there's a formula for this, Stirling's formula it's called. Equivalent square S is equal to 4 times the area divided by the perimeter. You could also write this out, 4 times L times W, that's the area, divided by the perimeter, which is 2 times L plus W. Or you could write this as 2 LW divided by L plus W. So whichever way is easier for you to remember. Let's work on an example. So say the width is 2 cm and the length is 9 cm. What's the equivalent square size S? So it's 4 times the area, 18, divided by the perimeter, 22. So 4 times 18 divided by 22, 3.3. Okay, so that's 3.3. So it's equivalent to a square where one side is 3.3 cm and the other side is also 3.3 cm. Those are radiologically equivalent for these calcs. So it's somewhere between 2 and 9, which is always the case here. So one final thing is that there may be some blocking in the field, like here as I showed before. And so then the question becomes, what is this equivalent square of this field, this open part here that's radiated? Some computer systems that do these calculations will estimate what the equivalent square is of this open field, and there are methods for this. I'm not going to go over those in detail because they're often done through software now, but a simple way to do it is to estimate what kind of rectangle would fit into the square, and you can estimate the equivalent square from that. Let me just mention this reference, AAPM Task Group Report number 71 from 2014, which describes monitor unit calculations for external beam photon and also electron beams. It gives you a lot more detail than what I just went over, but what I've given you are the essentials of this formalism and how to do a calculation. So those are the basics of the megavoltage beam dose calculation formalism and how you do a couple simple problems. I'm going to leave you with a little further reading reference material. But I do think that the way to learn this deeply is to do problems, as I said in the intro, so I encourage you to do that. In the next video, we're going to move on and talk a little bit more about some of the properties of these beams. We talked about that in video 10, the first video 10.1, but I'm going to go and talk about a little more detail. Okay, thank you.